Okay, we've now completed all the techniques that we need for integration. But what I want to do now is to do applications of integrations. The first one is when we're dealing with solids of revolutions. So let us begin and see what that means. So let us start off with. So the first important thing that I want you to remember is that if you've got a function like we do have here, you've got y equals to the square root of x. The function is covered by this particular blue curve over there. And I want you to think about if this was rotated in 3D, right? If this was made to be 3D, then it'll give you an entire solid. As you can see, this entire diagram can be translated as something looking like that in three-dimensional space. And what that does is that you can calculate this via these disks over here. So you can have a disk on top of another, on top of another disk, on top of another disk. But what can happen with this is that these disks, we are able to calculate the area of each disk and also hence the volume of each of these disks in three-dimensional space. So therefore, remember, an area of a curve in two-dimensional space can be turned into a solid if you put it into a three-dimensional space. So this is the first diagram that allows us to see that. So therefore, we are able, given an area in 2D, we are able to calculate its volume. So that because it can translate into a three-dimensional diagram. Similarly here, we've got a function here which is in form of a cubic function, but we can see that from 0 up until whatever the x values are, we are able to get this entire diagram here, put it into a three-dimensional space. So it'll just be this side alone, and I want you to see that in our case this is perfectly symmetrical. So therefore, we are able to then form these disks, and from these disks, because it's perfectly symmetrical up to 0 and the entire height of 8, we are able to calculate the volume of that. And that is absolutely important for us to understand. So therefore, without having to complicate your life, the formula to calculate the volume of solids is given. All right. So if you've got the area in terms of y, the volume of that is pi. You then have to take the lower bound and the upper bound. In symmetrical diagrams, you'll just have to take halfway through between that. And I'll show you exactly what we mean in our question. And therefore, we just need to square the function and then integrate that. So pi, the definite integral of the square of that function. And that's how you find the volume. Nothing complicated around that. There could be complicated types of examples, but that will depend on how you calculate your function over there. And those we will do when I tackle questions of this types in past papers. So let us dive right into it. So here I've got a quadratic equation. And in this quadratic equation, we've been asked to calculate the volume of this. So without having to stress too much, we need to find out what our boundaries are first. So I'll go y equals to 4x squared, and this can be split up into 2 plus x, and this can be split up into 2 minus x. So therefore, this means that this is -2 and this is 2. But because we can form these disks that I was talking about there, those disks will be able to help us calculate the volume. And therefore, based off of this is symmetrical, about 0. So therefore, when we're doing this, our boundaries will now be, our lower boundary A will be 0, and our upper boundary B will then be 2. So therefore, we can apply our formula for volume. So let's go. So this will be the volume is equals to pi, the integral going from 0 to 2 of y squared. So y squared is simply this expression all squared dx. And how do we square an expression like this? This is you square the last term, which is 16, double the product, which is minus 8x squared, plus the last, which is square the last term dx. And this is between 0 and 2. So this is a definite integral for sure. And then we can go about and see how will we integrate that. So to integrate that, remember basic functions. So this will be 16x. This will be 8x to the 3 divided by 3. This will be x to the 5 divided by 5. And therefore that is our integral. So therefore we'll now be taking the boundaries between 2 and 0. So remember, when we do this, we'll multiply everything by pi at the end. So this becomes 16 times 2 minus, so we sub in 2 in our initial one. And then we will do the same boundary minusing now. We will then multiply by, we'll have to sub in 0. So this is 0 there. Minus 8 times 0 cubed 3 plus 0 to the 5. And then I'm sure now you've guessed this right. This entire side here is going to be 0. And I think if we then plug this into our calculator, we are able to get, this will be pi. And if you plug this into your calculator, you'll get 256 over 15. Please verify with me. And therefore, we can say that the volume of that entire function will be 2 over 15 pi. And that is how we apply this. So what I will do, I will just confirm the different examples that we do using questions from past papers. But I think this concludes our understanding of how we can do the volume using integration. So this is solids of revolutions. I hope this has made sense, and therefore see you in the next video.